Hey guys, this is Kerry, and in this video we're going to look at the answer key for homework number 1. So hopefully this works out. So what is a bit? How are bits related to computer science? Bit is the most fundamental unit of information. It is either a 1 or a 0. In computer science, we use bits to represent all information. So movies, images, text, numbers. Every single thing your computer does is a bit. Even actions on your computer are represented using ones or zeros. Convert the following number from binary to decimal. So I write pretty big, so it's going to be helpful for me to recopy this. Just like you discovered in class today, it's helpful to think about these numbers as sort of columns in a table. So this is the ones place, the twos place, the fours place, the eights place. And the column we saw to get these place values is to multiply by 2 each time, so 16's place, and then 32nd's place. So it looks like in our case, we're going to have 132, 18, 14, 12. And if we combine all of these things together, we get the number 46. Alright, I'm going to be leaving problem 3 and 4 for you to do on your own because they're very similar to the one we just reviewed. For problem number 5, we're going to be doing the opposite of what we did before. Instead of converting a binary number to a decimal number, we're going to be starting with a normal decimal number and converting it to binary. So to do this, we do the exact same thing. We set up our bins, or our table columns. So we've got the ones place, the twos, the fours, the eights, the 16s, the 32nds, the 64ths, the 128ths, etc. And I think it's clear I've actually gone a little too high. In order to make 49, I won't be needing 128. I also won't be needing 64. I do need a 32 though. So when we're converting it from decimal to binary, we're kind of greedy and we use the largest possible numbers first. So it looks like we've got a 32. So let's see, I think it's helpful to keep a running tally here. So if we do 49 and we use a 32, then we have to make 17 more total. So to make 17 more total, it looks like we could use a 16 and we could use a 1. And we don't need anything of the others. And so our binary number answer will be 110001. This is the number 49 in binary. Let's do one more of these. Convert the number 172 to binary. So for 172, we'll set up our columns. 1s, 2s, 4s, 8s, 16s, 32nds, 64s, 128s, and then the next one would be 256, but I don't think we'll be needing that one. Alright, so let's see which ones we need. Well, we'll start with the largest possible number. We do need a 128. So if we do 172 minus 128, it looks like we're going to need 44 more in total. To make 44, we won't be needing any 64s. We do need a 32. And that means we need to make 12 more. So 8 and 4 is 12. And it looks like we won't be needing anything else. So our binary representation of 172 is 10101100. Convert the number 4 to binary. I think you got this now. On the image below, each row of the image is encoded in an 8-bit binary number. So here we go. This is 8 bits. It's binary because it's ones or zeros. Each one of the digits is a bit. Using zeros as black squares and ones as white squares, shade the pixels to create the encoded image. So let's see. So zeros are black squares, and I think I might have gotten it backwards, but it still looks pretty good. So let's just do this. All right. So then all the ones are white. And I'm going to leave the rest of it for you to discover. It actually looks pretty good if you're a little more careful with your shading. But what this problem highlights is you can use bits to encode images, as we hinted at in the interview project today. Now the last problem is a step up from the problem that we were just doing. In the image below, each row of the image is encoded using a single decimal number. So we've got regular numbers instead of binary numbers now. And in order to decode this, we have to go into a middle step. We have to convert this to a binary number. So let me just see. We've got a 1's place, a 2's place, a 4's place, an 8's place, 16's place, a 32nd's place, a 64's place, and a 128's place. Okay, so when I create my table, I'm going to be using all of those places. So 128, 64, 32, 16, 8, 4, 2, 1. And I think this organizational structure is actually very useful for this problem because we're going to have to convert all of these numbers using the same columns. So first off, we've got 66. So to convert 66, we don't need any of these. We do need a 64, but that leaves us needing 2 more. So 64 and 2 is 66. And the rest will be zeros. For 129, it looks like we need 1, 1, 1, 1, and nothing else. For 189, it looks like we'll need a 128, and maybe we need to do some scratch work over here. That leaves us needing 61 more. So we won't be needing any 64s. We do need a 32. That leaves us needing 29 more. So we'll need a 16, an 8, a 4, and a 1, I believe. All right, so I think that that's our 189. To make 90, we'll need 0 of these, 164, 0 32s. We will need a 16, and then we'll need 10 more, so an 8 and a 2. And the same way that we did before, we can actually shade these. So it looks like we're supposed to zeros as black squares, ones as white squares. So the first number 66 corresponds to this shading. The next one corresponds to this shading. The next one corresponds to this shading. The next one corresponds to this shading. Oh, wow. I shaded the wrong thing there. This shading. Let me restart that column, that row. So zeros are being colored in. And I'll leave the rest of this for you to discover, but this is another way of encoding pictures using binary. So hopefully you found this video helpful. And if you had any questions, hopefully it answered them. See you guys tomorrow.